So today, Dongyu will report his some work with me about prime butterflies. Please.
Yeah, thank you for introducing. And yeah, this is about the stronger version of third field theorem for vertex minor. So yeah, as he said, this is joint work with Sagil Ong, my advisor. And yeah, let's start. So let's review the third field theorem first. So many introductory class of the graph theory course introduced this theorem, which state that if graph is not isomorphic to a field, then it has an edge. A simple three connected graph has an edge such that G deleting E or G contracting E is also simple three connected. So a field graph looks like this. So a cycle with some additional vertex which adjacent to every original vertices. And if you consider this a limb, then if you contract this, then you can find two parallel edges, two parallel spokes. So this is not simple. And if you also contracting this spoke, then also you can find parallel edges. And if you deleting any edges from a field, then you can find the vertex of degree 2. So this is not simple three connected, And for this graph, if you contracting this red edge, then the graph is still simple three connected. And if you delete this blue edge, then the resulting graph is still simple three connected. And actually, you can find more edges satisfying this property. And we call such an edge, which is satisfying these properties, G deletion E or G contraction E is simple three connected. Then we call this edge non-essential edge in G. Okay, and this is proved in 1961 and quite long time ago. And in 2000, Oxley and Wu proved some stronger result. So for every simple three connected graph G, it has at least two non-essential edges if it is not isomorphic to a field. And also they characterize something more. So a graph is not isomorphic to none of field, a twisted field, and a multidimensional field, which looks like this graph. Then it has at least three non-essential edges. So let's see a twisted here. So if you contracting this red edge, then the resulting graph is still simple connected. And also for the other red edge. And if you contract or deleting any other edges, then the resulting graph is not simple three connected. And for this graph, this is called the multi-dimensional field. So this is k-dimensional field, and we assume that k is at least 3. And if you deleting this center edge, then the resulting graph is still simple three connected. So these two classes of graphs are the graphs, simple three connected graph with exactly two non-essential edges. Okay, so this is the formal result, and our result is about the vertex minor. So before introducing our result, we compare the result of some theorems about graph minors and vertex minors. So it is well known that in graph minor project, Robertson and Seymour proved that grid theorem and testing graph minor and Wellcourt's ordering. For more precisely, grid theorem states that every graph, if it has a large tree width, then it has a large grid minor, and Gillon, Kwon, and McCarthy, Orlan proved that some corresponding result for the vertex minor. So for the tree, rather than tree width, they use the length width. And also testing graph minor and Wellcourt's ordering, the corresponding result only proved for the graph class with bounded length width. And third field theorem, the corresponding result was proved by Ellis in 1994, and our result is correspond to the Oxley and Wood's theorem, which extend the third field theorem. So I think I need to review the concept of the vertex minor. I think IBS members are maybe familiar to vertex minors, right? But here some new, so some other.
Because I'm a little confused. Graph definition. So by 3 connected, you mean there's no vertex of size 3 or 2?
No vertex code of size 2. Yeah. Also, I sometimes confuse, and also you need to assume that there is at least 4 vertices. And okay, so let's review the concept of the vertex minor. So let's first define some operation G star V. The resulting graph is a graph obtained from G by complementing the induced subgraph of G induced by the neighbors of V. So if you look at this graph, and then the subgraph induced by the neighbor of V is path of length 3. And if you take a complementation of this, also the resulting graph is path of length 3, but with different order. So the resulting graph is this, okay? And we define 2 graphs are locally equivalent if one can be obtained from the other by applying a sequence of local complementation. So we call this operation is local complementation at V to G. And a graph H is a vertex minor of G if H is an induced subgraph of G locally equivalent to G. So for example, this graph is not an induced subgraph of this, but this is an vertex minor of G. And let's define another operation, so pivoting. So pivoting edges means here let E be an edge with ends V and W. And we define pivoting E. So this is equal to graph applying a local complementation at V and then local complementation at W and V. So consecutively. So here we have a graph G and there is a pivoting. This is a resulting graph. So okay, now I explain it more briefly. So the first set, the leftmost set is the neighbors of V, which is not W and also not the neighbor of W. And the center vertex of set is a common neighbor of V and W. And the rightmost one is the neighbor of W, which is not V and not neighbor of V. Then there is 3 bipartite graph obtained from a pair of two vertexes, here, this, and this. And as like the local complementation, we can complementing this bipartite graph. Then we obtain this graph. And after that, we swap the labels of V and W. This resulting graph is equal to this graph. So this operation called pivoting E on HE, and we define pivot equivalence and the pivot minors similarly. And we define one more weird relation, so G/V, and I will usually call it G pivot deletion V. So this is, if V is isolated vertex, then we just deleting each vertex. Deleting it, and if it has a neighbor W, then we define it as G pivot VW, pivoting VW, and deletion V. So of course, there is a lot of possibility of W. So V has possibly more than 2 neighbors. But fortunately, this G pivot VW and G pivot VW prime are pivot equivalents. This implies that whatever we choose the W and W prime, these two are pivot equivalent. So this notion is well defined up to pivot equivalence. So of course, well defined up to local equivalence. And Boucher proved the following. So every vertex minor on the VG minus small v is locally equivalent to one of these three graphs: deleting and pivot, local complementation and deleting, and pivot deletion. So you can remember that for the graph minor, there is two ways to reduce an edge. So contraction and deletion. And for the vertex minor, there is three ways to reduce a vertex. This and this and this. Okay. Okay, and you wonder that why we consider this kind of weird operations. So I will explain why this concept is useful. So I will compare the original minor relation of the graph and pivot minors of the bipartite graph. So let's consider this graph, G. I will call it G. And these red edges are the edge set of a spanning tree of G. 1, 2, 3, 4, 5, 6. And the remaining edges are A, B, C. And from this, we can build a bipartite graph. So the vertex set of this graph correspond to the edge set of this graph. And one partition is B, and the other partition is the remaining edges of G. And we give an incidence adjacency relation between two vertices. If from these red edges, when we add this blue edge A, then we can find 4 cycles. This is a unique cycle in this graph. So A, 3, 1, 2. And then we give an adjacency relation between A and 1, A and 2, A and 3. For B, we can find these 4 cycles. So we joining B and 3, B and 4, B and 5, and so on. So the resulting graph is this bipartite graph. And of course, there is a lot of choice of this B. Before that, I will call this graph with this graph, the fundamental graph of G with respect to B. And of course, there is a lot of choice of B. So we can choose this B symmetric difference 1A. This triangle means the symmetric difference. So we deleting 1 and adding A to B. Then the resulting fundamental graph looks like this. So 1 is incident with this, 2A3, and B is incident with adjacent to 3, 4, 5 in this graph, and C is adjacent with 5 vertices because it make a 6 cycle. Okay, so this is the fundamental graph of G with respect to another base. And you can easily check that these 2 fundamental graphs are pivot equivalent. So if you applying pivot equivalent, if you pivoting 1A, then A is only incident adjacent to 2 and 3 except 1, other than 1, and 1 is only incident with C, adjacent to C. So we join C and 2 and C and 3, and swapping the labels of A and 1. Then the resulting graph looks like this. So these are same. So this means that if you choose some another B, then we can find another fundamental graph which is pivot equivalent to the original one. And also you can find some relation between the deletion of edges in here and deletion of vertex here. And also you can find, if you're contracting 1, then it corresponds to this, deleting 1. And so depending on this element is in B or not in the B, we can find this kind of relation. So this means that FGB deleting 1 is a fundamental graph of G contracting 1, and this graph is also fundamental graph of this, okay, and so on. So there is a good relation between them. So you can consider bipartite with graph with pivot minor relation is kind of concept related with graph minor. And since vertex minor contains a pivot minor relation, so this is kind of generalized concept. Okay, now I will introduce prime graphs, which correspond to the concept of the three connected graph in the graph minor relation. So when we prove many problems in graph minor related with graph minors, we can usually assume that some minimal counter example is connected. And sometimes we can assume that the minimal counter example is three connected. And actually prime graph behave similarly in graphs with vertex minor setting. So a vertex bipartition of xy of G is split if each part is at least 2 and the edges between x and y is just a complete bipartite graph. So it looks like this. So here is x and here is y, and this is a complete bipartite graph. Then we call this a split. And a graph is prime if it has no split. And for example, you can check that every graph with 4 vertices are not prime. For example, C4, cycle of length 4, is not prime because if you consider this x and y, then this is complete bipartite graph. And if you consider path of length 3, then this x and y, then you can see that this is a split. So there is no, and checking other graphs, you can get this result. And also you can check that every prime graph with at least 5 vertices has no vertex of degree n-1 and also has no twin. So twin is a vertex which 2 vertices which have same neighbors other than themselves. And Boucher proved that if xy is a split of G, then it is also a split of a graph locally equivalent to G, and therefore every local equivalent graph of a prime graph is prime. Now I finish to introduce the setup, and now I will introduce the corresponding result of third field theorem for vertex minor. So we said a vertex V of G, here vertex, not the edge, is non-essential if at least 2 of these 3 ways to reducing a vertex are prime. And note that 2 graphs are locally equivalent, then the set of non-essential vertices are same. And Ellis proved that every prime graph with at least 5 vertices has a non-essential vertex unless it is locally equivalent to a cycle. And what he proved that actually this graph has at least 2 non-essential vertices. And you can easily check that every cycle graph of length at least 5 is prime and has no non-essential vertex. So if you delete V, then this is not prime. And also, if you consider pivot deletion V, then this is also a path, so it is not prime. So this gives maybe you can understand it as a if and only if condition. And
why non-essential is just at least 2 of them?
Yeah, good question. So one of my original motivation is related with my personal motivation is related with the PU to find the minimal obstruction of the PU-orientable graph. So this is more related with the pivot minor relation, not the vertex minor relation. So if you have two of these are prime, then you can say, oh, at least this or this is prime, right? And you can check that this is a pivot minor of G on Vg minus V. So this is still meaningful to understand the pivot minor. So, okay, and also this is actually related with our corollary. So we define a vertex V is non-pivotal if one of two are prime. And trivially, every non-essential vertex is non-pivotal. And if we limit our focus on only the bipartite graph, then we can prove something more. So if G is prime bipartite graph, then the other direction is odd. So for this graph G, non-pivotal and non-essential is actually same. And also you can check that bipartite graph is locally equivalent to a cycle if and only if it is pivot equivalent to an even cycle. And from our first main result, we can obtain the following result. So every prime bipartite graph with at least 5 vertices has at least 2 non-pivotal vertices. If and only if it is not pivot equivalent to an even cycle. So you can remember that there is a relation between the bipartite graph with pivot minor relation and a graph with the graph minor relation. So this is quite good to understand. Actually, this implies the third field theorem. So for binary metroid and for graph, both. So here in this talk, I want to avoid to explain the metroid concept. So this is easy. So if the graph is not pivot equivalent to an even cycle, then by the second lemma, this is not locally equivalent to a cycle. And because of our first theorem, it has at least 2 non-essential vertices, and because of first one, we can deduce that, oh, it has at least 2 non-pivotal vertices. And you can prove the converse similarly. And yeah, this corollary implies the third field theorem. I mean, stronger version of third field theorem proved by Osley and Wu. This is this proof skips many details, but by considering here G is simply connected with graph with n, and most one non-essential edge, then we can consider its fundamental graph, FGB. Then I will skip detail, but this implies that this non-essential edge corresponds to the non-pivotal vertex in this graph. So we have at most one non-pivotal vertex, and this implies that this F is pivot equivalent to even cycle, and eventually this implies that G is a wheel graph. Okay, if you consider a wheel graph, looks like, so for example, this is wheel phi, and if you take B or B prime in here as this is B prime, then you can easily check that this is a, so here these two edges correspond to here 2 vertices, and this is instant with this. And yeah, this, if you consider this, then this is instant with this, and so on. You can check that, this is cycle of length 10. And also you can prove the other direction. Okay. And our second main result is this. So we also find the condition that a prime graph has at least 3 non-essential vertices. So our graph has at least 3 non-essential vertices if and only if it is not locally equivalent to this graph. So this graph means here we have 2 end vertex U and D, and there are at least 2 internally disjoint vertices from U to V, and the length of each path are at least 3 except 1. So the length of Pi is not equal to 2. And we all know, maybe if we enumerate this as a non-increasing order of the length, then possibly it is possible to P1, length of the P1 is 1. But except that every path has a length at least 3. Okay. The reason is that if you consider a graph with lots of these internally disjoint paths, and if you can find a vertex, if you can find a path with length 2, then you can show that this vertex is also non-essential vertex. So this graph has at least, actually exactly 3 non-essential vertices. So this is not for the backward condition. So okay, I finished to introduce our result, and now I will try to sketch our proof. So before that, I need to introduce the isotropic system, which is firstly introduced by Boucher in his series of papers. This is a purely linear algebraic object. So maybe it is hard to understand at first time, but this is very useful since it captures the local equivalence of the graph. Okay. So let K be a 2-dimensional vector space over the binary field. So here, these non-zero elements alpha, beta, gamma satisfying these equalities. Or if you can understand alpha, beta, gamma as like this in this vector space. And we define a bilinear form on K. X, y is equal to 1 if and only if both x and y are non-zero and distinct. And let KV be the set of vectors. Or you can understand this vector as a functions from V to K. Then this is this is 2V dimensional vector space. And also you can extend the bilinear form to K to the V. So 2 vectors A, B is the value of this bilinear form is nothing but just summation. Okay. Then for a subspace L, we can define its orthogonal complement of L with respect to the previous bilinear form. And we call subspace is totally isotropic if every elements of every 2 vectors in L are orthogonal to each other. In other words, L is a subspace of its complement, its orthogonal complement. And some linear algebra fact, we know that dimension of L plus dimension of its orthogonal complement is always equal to this if bilinear form satisfying some good properties. And if L is a totally isotropic system, then this is a subspace of its orthogonal complement. So this implies that this summation of this is larger or equal than the 2 times dimension of L. So this implies this. Now we define an isotropic system. It is a pair of a finite set V and L, which is a totally isotropic subspace of KV, which achieve the equality here. So it is good to see an example. So maybe this is maybe you can remember some definition of the isotropic system. So let's look at this. It's more important. So we have a graph G, whose vertices are 1, 2, 3, 4, 5. Do not care about this colored vertex and edges. And you can, from this graph, you can build some matrix-like object. So every diagonal entries are assigned by beta, which is a non-zero element of K. And for the non-diagonal entries, we assign alpha if this 1, 2 are adjacent. And if we assign diagonal entries as 0 if the corresponding two vertices are non-adjacent. And now we consider each rows. So first row is V1, second row is V2, and so on. And from these 5 vectors in KB, we can consider a subspace L, which is spanned by V1, V2, V3, V5. Then you can easily check that the dimension of this L is 5 because of this beta in the diagonal entries. And also, it is totally isotropic, since if you consider the bilinear form of V1 and V2, you can check that alpha beta, the result is 1, and this is for the I don't know. Oh yeah. Thank you. So if you comparing V1 and V2, so the first coordinate, then you can obtain 1, and for the second coordinate, you obtain also 1. So 1 plus 1 is 0 in the binary field, and so the value of this bilinear form is 0, and this also holds for any Vi and Vj. Therefore, we deduce that this L is totally isotropic. So we can define an isotropic system from a graph. Okay, and we say this G and vector A and B. Here, A is a vector whose every entries are alpha, and B is a vector whose every entries are beta. We define because of these diagonal entries and some non-zero non-diagonal entries. And we call this GAB is a graphic presentation of an isotropic system V, L. Okay, so you need to remember that we can define an isotropic system from a graph. And conversely, we can also construct a graph from an isotropic system. To do that, we need to find some special vector, which is called Eulerian vector of an isotropic system, which is satisfying this condition. So vector A itself is not in L, and also its restriction on any non-empty sets. So AX is defined as follows. This is also not in L. And if we have this special kind, and Boucher proved that every isotropic system has this special type of vector. And if we have for the given isotropic system and its Eulerian vector A, then we can find a graph G and a vector B satisfying some certain conditions. This implies that if you consider alpha and beta, then this is 1. So this means that the AV and BV is non-zero and distinct. And we can find this triple, G and B, which is satisfying GAB, is a graphic presentation of S. Okay, so if we have an S and A, then we can find G and beta, G and B satisfying these conditions. And we call G the fundamental graph of S with respect to this Eulerian vector A. And Boucher proved that every fundamental graphs of an isotropic systems are locally equivalent to each other. So this is a very good observation. So this is why we why we consider the isotropic system. And also we need to define the minors of an isotropic system. So LV alpha is a projection of the vector in A on V minus small b, whose V coordinate value is alpha or 0. So this is a subspace of KV minus small b. And if you consider a pair, this pair, then this satisfies every axioms of the isotropic system. So this is also an isotropic system. And you can define SV beta, SV gamma similarly. And we define a minor of isotropic system as follows. So one is a minor of the other if S prime can be obtained from S by applying kind of elementary operation of the minors. And Boucher proved that a relation between the minors of a graph and minors of an isotropic system. So let's assume GAB, this triple, is a graphic presentation of S. And then G deleting V is a fundamental graph of SVAB. And G pivot deletion V corresponds to GB, BB. And G local complementation and deletion B correspond to this. So we have three kinds of minors for the isotropic system, and also we have three kinds of minors for the vertex minor relation, and they have a good correspondence between them. Okay. So now I sketch our proof. So now let's assume that G is a prime graph with NS5 vertices, and let S be an isotropic system which has G as a fundamental graph. Or you can assume that SGAB for some vector A and B, S is an isotropic system. And we call a vector T is a triangle if its support is 3. Here, support means that some non-zero entries. So, for example, here, the support of V1 is 1, 1, and 2, and support of V4 is 3, 4, 5, okay? And if we assume G is prime graph, then the isotropic system obtained from G has no vector of such that whose support has size 1 or 2. So triangle is kind of smallest vector. I mean, the vector which has smallest support, except trivial vector. And Alice proved some kind of this result. So first, if we have two triangles, then support of them are disjoint. Or if they share one vertex, then the value of that coordinate must be same. And if they share two vertices, then each values are distinct, needs to be distinct. And if the support of T and T prime are same, then actually the vectors are same. So now from this lemma, the following, we can define a 3 uniform hypergraph. So this is 3 uniform hypergraph, H be a 3 uniform hypergraph with same vertex set. And each H set is the support of triangles in S. So because of this lemma, each H exactly correspond to there is one-to-one correspondence between the edge of H and the triangles of S. And we have lots of good properties of H. So the first property is if you have the first property is if V is an essential vertex. Essential means not non-essential. Essential vertex, then there is an edge in H which contains V. And the second property is if we have an HE and it has an vertex V which is essential. And also it has another vertex which is also essential. So it contains at least two non-essential vertex. Then we can find an edge which contains V and also contains some another vertex. So for example, this we have this or this edge. Okay. And third property is if we have two vertex, then there is at most three vertex which share these two vertices. And the fourth property is if we have two edges which share two vertices, and if we have an edge which contains one of these common neighbor, then it must be this or this or this. Okay. From these kind of properties, we can force some structure of the edge. And I will state it later. And now I will define some paths in three uniform hypergraph. So we call it a tight path P is nothing but looks like this. So with a vertex sequence, it has a consecutive edges. So for example, here this has 3, 1, 2, 3, 4, 5 vertices, and it has 3 consecutive edges. Looks like that, and we call this tight path of length k, length 3. Okay, and one observation is every internal vertices 1, 2, 3, or 1, 2, 3 k are essential in G. And we don't know their ends are essential or non-essential. But if one end is essential, then we can enlarge the path. Okay. So if you consider our second properties of H, then since V4 is essential, then we can find an edge which contains this and share two edges with V2, V3, V4. And if you check more briefly, then you can enlarge this. Okay. From this concept, we can prove our first main theorem. So remember, the first main theorem was if you graph has at least two non-essential vertices, then it is if and only if it is not locally equivalent to a cycle. And we prove a contrapositive argument. So if G has at most one non-essential vertex, then I will prove that this is locally equivalent to a cycle. So it has actually no non-essential vertex. So let's take maximal tight path first. Then you can check that these are all vertices of G. And since G has at most one non-essential vertex, either V0 or Vk plus 1 is essential. And by symmetry, I will assume Vk plus 1 is essential. And still, we can still applying this second property. So we can still try to enlarge this path. But unfortunately, we have no more edges, no more vertex. So this new triangle must contains this. Then, and if you can remember this matrix like form from the graph, so I will build a graph from this matrix-like form. So T1 has support V0, V1, V2. So this is this, and by some symmetry of non-zero elements of K, we can assign it as a this, and also T2, T3, we can assign it as a like this. And we know we obtain here new vector T here. And actually, since V has K plus 2 vertices, V0 to Vk plus 1, and there is only K and one more, so K plus 1 vectors. Since the dimension of L is one more than tier vectors here, so we can find some another vector, T prime, which T prime and T1 to the Tk and T form a basis of L. And you can, I will skip detail, but this must be for zero coordinate. This need not to be equal alpha. And if you only consider this, so V0, V2 to Vk, then you only consider this restricted matrix, then you can check that these entries, these rows of the restricted matrix from V2 to Vk is independent. So from this result, we can assume that T prime is 0 for here, and so it is also triangle, and we can find the Eulerian vector A and some corresponding vector B, and therefore we deduce that Ck plus 2, A, B is a graphic presentation of an isotropic system S. And since we take an S which has a G as a fundamental graph, so G and Ck plus 2 both are fundamental graphs of S, so we can deduce that two graphs are locally equivalent. Okay, and in the previous proof, if we try to enlarge the maximal type path, and if one of ends for the maximal type path, one of ends are essential, then actually we can deduce that this force that graph is locally equivalent to cycle. Then if we assume that G is not locally equivalent to cycle, then we obtain a result that V0 and Vk plus 1, both ends are actually non-essential in G. And if this is only for K is NS2, because K is NS2, then two ends are determined, but if K is 1, then by symmetry, we can choose at least two of them are non-essential. And from this, we can deduce the following some structural result on H. So if G is not locally equivalent to cycle, here N is the set of non-essential vertices of G. Then H is the union of these subgraphs, partial hypergraphs. Okay, so N here is nothing but the maximal type path of length N is 2, and N triangle is something like some maximal type path of length 1, whose every ends are non-essential. And windmill is a union of maximal type path of length 1, and tripod is union of 3 maximal type paths of length 2. So if you consider here red and green, this is a type path, this is also type path, and this is also type path. And also N table, you can see that red, yellow, green, this is a type path of length 3. And you can find 3 type paths of length 3 in here. And this implies the following result. So if we take 2 maximal type paths of H, then the set of non-edge vertex are equal of this joint. Okay. Now 10 minutes left. So I sketch our second main theorem, proof of the second main theorem. So, okay, let's remind its statement. So, I will write contrapositive argument. So G has at most two non-essential vertices if and only if G is locally equivalent to this graph, such that every path has length, no path has length 2. So suppose that G has at most two non-essential vertices, and by our first result, if G has at most one non-essential vertices, then G is locally equivalent to a cycle CK. And you can understand cycle CK as two paths of length 1 and k minus 1. So it is already done, so we may assume that G is not locally equivalent to a cycle. Hence, so G has exactly two non-essential vertices, and we denoted U and V. And by our corollary, we can partition this non-essential vertices, the set of essential vertices of G, by the internal vertices of the maximal tight path of in H. And so here, we have U and V, which are non-essential in G, and here P2 is these edges with 3 vertices, and here the orange one is the second edge of P2, and yellow one is the third edge, and so on. So this already gives almost right structure of G, right? So actually by taking some suitable good Eulerian vector, we can guarantee that G is locally equivalent to this graph. We call this as a theta L1 dot theta Lm. And as I say before, if the length of this is 2, then you can check that this vertex is also non-essential. So this graph has at least actually exactly 3 non-essential vertex, so which is a contradiction, which is impossible. So every Li is not equal to 2. So this means that except one, every Li is at least 3. Okay, this is end of my talk, and I will close my talk with some questions. So first one is, I only characterize the non-essential vertices with 0, 1, and 2. Actually, non-essential prime graphs with exactly 0 non-essential vertices is a cycle, and there is no graph which has exactly 1 non-essential vertex. And we also characterize a prime graph with exactly 2 non-essential vertices. Here, U and V are non-essential. And so if you characterize something more, then also it would be good. And I think this is not that hard because of our structural theorem for the 3 uniform hypergraph H. But one hard thing is find a suitable Eulerian vector. And the second result is, actually we didn't prove the corollary of main 2, which correspond to the graph minor result. So if you can prove this, if you can prove this second question, then I think this is also good. And my third question is actually related with my personal motivation. So if you can find 2 non-pivotal vertices U and V satisfying this additional condition, then I think this is a very good tool for finding a minimal obstruction of the PU orientable graph. So yeah, this is end of my talk. Thank you.
Any questions?
Yeah.
When you make a fundamental graph, you choose B as an set of G.
Yes.
So what's the condition of B?
B must be spanning edge set of the spanning tree. So when G is connected, so because then if we add an edge outside from B, then there is a unique cycle. So it is, you can find this. You can define F. Maybe I give one comment about our result. Actually, Oxley and Wu's result are proved in terms of the Metroid, more general concept. So this is very special version of their result. Only is restricted on the graphic Metroid.
Questions? Right, finish that. Let's take this